This is UCF Student Rocket Launch Initiative, Red Team. I am Andrew Nino, a component engineer, and I was responsible for the nose cone and electronics.
I'm Interior Williams, and my part was the airframe.
I'm Jack Coulter, and my part was the fins.
I'm Devin Pierce, and I was in charge of the recovery system.
Our other teammate Kevin wasn't able to make it today, but he had a big role in the motor selection and payload.
So our mission for this project was to design and launch a payload-bearing rocket that is capable of reaching 2,000 feet. We were also to maximize payload carrying capacity in the system and integrate payload remotely from a distance of at least 3 feet, recover the system in reusable condition, and also in a 1-mile radius.
So the impact of our project, our primary application for the project was to provide a proof of concept for a Mars sample return mission with the launch and return of a rocket carrying liquid sample capsules. Our secondary application was to provide a proof of concept for a reusable rocket capable of launching commercial satellites and small payloads. The overall impact for our project was to create a payload-centric design where a higher percentage of the system's mass lies in the payload.
Our solution was to minimize the weight of the entire system by using a tapered system design with lighter building materials, which would allow us to carry a higher payload mass. We elected for a dual deployment recovery system because this leads to a higher rate of recovery and reusability, which is extremely important for this project. We also utilized a high impulse launch with a short burn time so that we can carry significantly more payload mass. And we used a gravity-based loading system for the payload to ensure that everything went in properly and smoothly.
This is a brief overview of our system. It's a 6.5 foot tall rocket. The total system weight is 11 pounds, with 2 pounds of it being payload. This is really big because it's 18% of the total weight, and in most rockets, payload is only around 2% of the total weight. Our taper, as we mentioned earlier, is a 4-inch to a 3.1-inch outer diameter change. Our airframe is reinforced with carbon fiber and fiberglass. We have an electronically dual deployed parachute, and we have modular fins. So now we'll talk a little bit about our design. This is the early stages of our design. Most of the stuff that we based our design off of were commercially available airframes. We then simulated straight and tapered designs in Open Rocket, as well as tested different motor classes and motors to gauge what the system would reach as a preliminary measure. With this design, we were able to set parameters like system weight and length.
For modeling in our project, we primarily used it for non-COTS airframe structures, such as the nose cone, the payload carrier, the fins, and the transition piece. These models were guided by early design parameters that were given to us, and by designing and modeling these parts, it allowed for simulations and optimizations to ensure that they could withstand the forces endured during the flight.
So simulations were a really big part of this project. We use things like CFD, FEA, and Open Rocket. CFD and Open Rocket were mainly used for optimization purposes. As you can see on the right, we tested different nose cone shapes to see which one would reduce the drag the most, as well as looking at different fin shapes to see what would reduce the drag the most and up our stability. Besides optimization, it was also really important to do stress analysis. We were able to detect the weakest point of our system, which is the taper, and then run a stress analysis on it to see what would happen, what would need to happen in order for a critical failure to occur. Simulations also occurred in an iterative process. We would constantly, as we were manufacturing, input new weights, new lengths into Open Rocket simulation to constantly get up-to-date statistics on our overall apogee and system performance.
Our manufacturing process included 3D printed components as well as commercial components. 3D printed components included the nose cone, fins, payload capsule, and transition pieces, as well. Well, for the commercial components, it was craft paper body tube, reinforced with carbon fiber as well as fiberglass for additional strength. The recovery system and other components included the laser cut sintering rings.
So for our testing process, we first dry fit all the sections together to ensure that they would not come apart extremely easily. We then tested the airframe by conducting load testing on critical structures such as the transition and payload carriers, so we could ensure that they would withstand the stresses we expect them to face. In our next video clip, you'll see our testing of the payload section so that we could ensure that the payload vessels would properly fit within the carrier we designed. And we also tested the integration system multiple times to ensure that the payload would go in smoothly and without issue.
3, 2, 1.
And for our final video clip before we go to the launch site, you'll see us testing the ejection charges for the recovery system. We did this multiple times with black powder weights ranging from 0.486 to 1.7 grams. And through this testing, we were able to determine that 1.5 and 1.7 grams were sufficient for the lower and upper section ejections, respectively.
And now with all that design work done, we can go look at the components in their matured states on the field. So this is the top of the rocket. It's our nose cone. In the final design, we added a shoulder, as well as internally we ballasted it with clay, and we have our beeper on the inside. And the final shape that we decided on is an elliptical nose cone because it reduced the drag the most on the rocket.
This is one of our main body tubes. I wrapped it in carbon fiber as well as fiberglass using epoxy wet layup. The outer diameter of this tube is 4 inches and the inner diameter is 3.9 inches. Alright, so this is our second body tube. It is approximately 3.1 inches outer diameter. It is also reinforced with carbon fiber and fiberglass, and it is bright orange for easy recovery.
This is our payload capsule. It weighs about 4¼ pounds, and about 2¼ of that is the actual payload. You've got a modular design since we didn't know what our final weight would be until like very close to launch. So you have these 3D printed sections, you stack them up, and you push all the payload capsules in. They're all secured by a threaded rod, which also carries the force of the parachute shock, which will be attached here. The top is secured with thread locker, and the bottom is secured by snugging 2 bolts against each other. The payload is these ping pong balls that were provided by our advisor. They're all half full of water. We were given permission to make them stop leaking in the container, like they spill without any force, so we've hot glued every single one of them closed. But that won't protect them from the forces of flight and recovery, which is why we have this gigantic payload capsule to protect them all.
This is the transition piece for our body tube. It is printed out of PETG plastic for durability. When you open it up, you can see that all the electronics are on a sled mechanism. There's threaded rods running through it, running to the bulkhead. And then in the bulkhead, you'll have igniter sticking out with our black powder. The top is secured with wing nuts, and this eye bolt is for parachute and shock cord, and it is thread lockered and epoxied on it. Besides that, we have a switch on the outside to arm the electronics on the pad, and this seals up nicely with the lower half tapered section. So yeah, that is our transition piece.
Alright, so we got our parachutes right here. This is our main. It's going to be 58 inches fully unfolded, and our drogue chute with a nice quick link on the bottom for 36 inches with a spill hole. And we've got a Kevlar shock cord here for fire resistance, taped to dissipate energy, and a fire blanket to not burn the parachutes.
Alright, so for our final design, these are modular fins. As you can see, we have tapered swept and then rectangular. We double nutted the fins so they were very secure, and then we trimmed off the rest of the screw. And there's a little bit space right here, so we just shimmed it and filled it in.
And there it is.
5, 4, 3, 2, 1, launch.